So hello everyone, I'm Norman Wildberger. We're here at the University of New South Wales. And today's talk on the history of mathematics, we're going to look at ancient astronomy and go back to ancient Babylonia and to the Chinese. So this is a topic that we've talked a little bit about before in this series. We've talked a little bit about Greek astronomy, some earlier video. But it's a big subject because classical astronomy really figures really prominently in the history of mathematics. It's not much of an exaggeration to say that mathematicians and astronomers were almost the same things for a few thousand years. So if you were an astronomer, you were a mathematician. If you were a mathematician, you were an astronomer. And that's in fact carried on even into relatively modern times. Newton, Euler, Gauss, Laplace, many prominent modern European mathematicians were also very interested in astronomy. So, but if we go back to the earlier times, there's an obvious reason why primitive peoples and early cultures would have been interested in astronomy. First of all, because if you're living around the Mediterranean region, the night sky is there for quite a long time. You've got almost 12 hours of darkness, and since human beings usually sleep for about 8 hours, that means that you're awake for quite a few hours when it's dark. And you may have some fires and such, but otherwise there's this night sky that gives you something to look at, and it's sort of interesting. So people would have sat around fires and looked at the night sky for hundreds of thousands of years, and would have kind of looked and speculated as to what was going on up there. And so this is the basic question, what's going on in the night sky? And this rather abstract question has connections with certainly calendar keeping. So if you want to have a calendar that's based on the year, then you're going to base it on the stars. So any kind of reckoning of time has to be somehow connected with a knowledge of what's going on in the night sky. So calendar reckoning was certainly one important reason in order to, for example, predict floods or regular occurrences, but also those religious reasons, religious or maybe philosophical reasons. Many ancient cultures, modern cultures too, sort of think of the gods perhaps as somehow being associated with the heavens, and so this connection between heaven and earth is a sort of a naturally important one in our spiritual understanding. And so it's natural to try to understand what's going on up there with the idea that maybe it can influence what's happening here on Earth. There's also a kind of a reason having to do with regularity, that one observes that when one's looking at the night sky, there's a certain regularity, there's a kind of pattern there, which is both interesting and subtle. And the more carefully you look at it, the subtler it starts to appear. You start noticing things that maybe you didn't notice the first few years you were looking. So there's some regularity, but also combined with some irregularity, or maybe we could say sporadic, or maybe almost mysterious events or movements. So some things are pretty regular, but against that background of regularity, there are these rather unpredictable things. So for example, there were, well, the motions of the planets. The planets were different from the stars because they moved around in some rather unpredictable way. Then there were comets. And of course there's the sun and the moon, which of course I suppose one should mention first of all, but they're actually quite regular. And their pattern you can establish after a few generations of careful study. But then after planets and comets, we also have other things like occasionally there's star explosions that occur, where you have what we now regard as supernovae, where stars explode, and for a few weeks there's some very dramatic things going on. And there's also very prominently eclipses eclipses both lunar and solar. And these eclipses would also have had a very profound sort of spiritual effect on human beings, especially the solar ones where the sun is eclipsed and everything becomes really dark. That's very scary, potentially, for people. Okay, so there's all kinds of interesting things going on with the night sky. And I suppose a good place to start for us in studying how the ancients thought about things is probably to review our current understanding. Okay? So this is not the understanding that they have. This is an understanding that only gradually became apparent after thousands of years of thinking and observation. But it's probably a good reference frame because this is something that's more or less familiar to all of us. So the current model of what's going on is a heliocentric model where helio means sun, so things are revolving around the sun. And so let's review that. Maybe I'll draw a rough picture. So here's the sun. And then around the sun we have our various planets that are moving in, well, they're actually elliptic orbits, but they're pretty close to being circular, but not quite. So the innermost planet is Mercury. And this is not to scale. And then we have Venus a little bit further out. And then we have our favorite planet, Earth. And then Mars. And then further out we have the two gas giants, Jupiter. It's bigger. And Saturn. So for most of antiquity, the other planets, Uranus and Neptune, were not known. So these were the main objects, along with, of course, the moon, which we should put around here. So around the Earth, we have our own little satellite, the moon, which goes around the Earth. There it is there. So that's our modern view, roughly. That we have the sun in the middle and these various planets going around the sun in elliptical paths, but which are almost circular. And they're all essentially in a plane. Okay, they're all pretty well in a plane. And they're all going around, I think, pretty well in the sort of the same kind of direction. So let's have a look at this a little bit more closely. In particular, what's happening to the Earth. Okay, so here we have the sun again. And over here is planet Earth. And let's just concentrate on its orbit. So it's going around. Here's Earth. And maybe I will put its north pole here like this, and its equator here. It's actually somewhat tilted to the plane of this circular orbit, and it's going around like this. And so maybe the dominant thing is that the Earth revolves once around the sun in a year. And it revolves or rotates once on its axis, the north-south axis, in a day. Okay, so it's going around here, and that takes 365 point some years, some days rather. I don't know what exactly. And at the same time, it's also spinning on this axis, and it goes around once a day, 1 day to go around. And then we have the moon, and the moon is going around also more or less in a circular fashion. So there's the moon, And it's also going in this direction. And it goes around the Earth in around 27.3 days, so around 28 days or so it takes for the moon to go around the Earth. Okay, so let's have a look at this. Here's a little model. So there is the sun, let us say, and here is the Earth. Okay, and you see I've drawn a red spot on the top of the Earth. That's the North Pole. And there's an equator there, and maybe you can see someone, maybe that's you. Okay, although here in Australia we'd be down there, but all right. So the Earth is, let's say that we're happening sort of to look down on the situation, so we're looking down on the North Pole, more or less, of the Earth. So the Earth is rotating around the sun in this circular fashion, goes all the way around the sun in 1 year. And at the same time, it's spinning on its axis, and it's rotating this way in the same way that it's going around this way. So it's going around its axis like this, and it takes 1 day. So from there to there is 24 hours. And in that 24 hours, of course, it's gone a little bit along its yearly orbit around the sun. Now, things are a little bit complicated because the Earth is not straight up and down like this. The North Pole is not directly pointing up in the plane of its orbit. It's actually tilted. Okay, so it's tilted like this. And this tilt is a very important thing. It's about 23 point something degree, maybe 23 and a half degrees. Okay, so that's how far the North Pole's axis, the axis of the Earth, is tilted from the perpendicular axis of the plane in which it's moving. It's moving in a plane. We could make it the table here if we don't want to, but and then there's an angle here. Okay. And then around it we have the moon. Let's say that's the moon. Okay. So the moon is also going around the Earth, and it's also going in that same kind of direction. So if you were looking down, all these directions are counterclockwise. The motion of the Earth around the sun, the rotation of the Earth on its axis, and the movement of the moon around the Earth are all going in this direction. Okay, so the moon is going around like this, so the Earth takes 1 day to go around like this. In that time, the moon has moved 1/30 of the, or 1/28 of the way around. Okay, so in 1 day, the moon will go from here to here. As the Earth goes around once in 1 day, the moon goes around a little bit like this. And then when we're a little bit further along the way around the whole thing. Right? So these are the main features. The fact that we have more or less a stationary sun. We can assume the sun is stationary. The Earth is moving in these two kinds of fashions. And then we have this satellite, the moon. And then, of course, there are these other planets which are doing their thing. There's Mercury going around here, and Venus going around here, and Mars a little bit further out. And then way over there, there's Jupiter making a bigger circle, and Saturn making a bigger circle around it. Okay. And those planets, Mercury, Venus, Mars, Jupiter, and Saturn, are all visible to us with the naked eye. We can see them. And we can see them as bright lights. And you will notice that as we're moving along here, right, the plane of our rotation is also more or less the plane on which all these other planets are. So these planets are not up there. They're all more or less in this plane. Not quite, but more or less. So that means as we're looking, as we're looking in the night sky, the planets are all likely to be along some relatively narrow band. Okay. Now, so there's these two kinds of movements. There's a revolution around the sun, and there's the rotation around the axis. But there's also a third kind of movement, which is much more subtle. And that third movement is also coming from antiquity. It was actually discovered by Hipparchus, ancient Greek, probably the most prominent ancient Greek astronomer. And that's the precession of the equinoxes. Okay, what that amounts to is that the Earth is actually, the Earth's axis is actually wobbling. It's much the same as a top. So you'll all have spun a top, right? You know, you get a top and you spin it like this, and it's spinning there like this. And eventually, maybe you hit the top, or it starts to make this kind of motion like this. At the same time as it's spinning very fast, its axis is actually wobbling. Right? So if you actually looked at its axis, imagine a spinning top, and at the same time as it's spinning, the axis is going around like that. Have you ever witnessed that? Next time you have a top, spin it, and you'll see, I mean, they're not always straight up and down, and if they sort of started a thing, they'll wobble around like this. So what that means is that the Earth is doing the same kind of thing. That this axis that is 23 degrees from the sort of vertical of the plane of the Earth is actually itself making a rotational movement. So there's a further circle in this direction. Okay. Which means that the North Pole, the direction of the North Pole is actually changing. And how often does that change? Well, that takes about 26,000 years. Or about 1 degree in 71 years. So that means that maybe at this period of time, if you're in the north, if you're tilted this way, that means this is the summer season. And then as you rotate around and you come over to this side, then that's the winter season, okay, if you're in the northern hemisphere. So what that means is that in another 13,000 years, things will have changed. And when you're over here, the axis will actually be in this direction. And so this same place where the Earth is now, it will, instead of registering as being summertime, it will actually be wintertime. And that's very noticeable if you're watching the sky, because the constellations that are visible to you change from different parts of the year. Right? If we're looking in this region here, we can see part of the rest of the night sky. Right? After all, we're not just the solar system here. There's also all these other stars, which are many thousands of miles away, even in this kind of scale. But so these fixed stars, some of them are visible to us and some of them aren't. So if we're like this here, and things are tilted like this, then people who are on this side are experiencing nighttime because the sun is not visible to them. So this is the bright side, the daytime side, and this is the nighttime. So anybody over here will be looking out here and seeing those as the stars, the nighttime stars. So if you're over here, you're looking out and you see all those stars, and that's the night sky. Okay? But when you're over here and the seasons have reversed, now you're still there. Now the night time is the time that's shaded. So now the sun is lighting up this half, and this is the dark half. So now if you're sleeping and you go outside and you look out in the night sky, you're looking at those stars. Okay? So you're seeing a different kind of set of stars than you do in the summertime. And over the 26,000 year period, those things will change. They'll interchange each other. So this was noticed, this precession of the equinoxes was noticed first by Hipparchus, who was a prominent Greek geometer, about 129 BC. And the reason, how would he have noticed this? So he noticed this because he was comparing his records to earlier Babylonian records. Okay, so the Babylonians had been doing astronomy already for quite some time when the ancient Greeks came around. So even Hipparchus, who was sort of a pioneer of astronomy, he had these earlier Babylonian tables to look at, and he could see that their descriptions of where various constellations were at various times of the year was a little bit out from what he could observe. right? We're talking about 1 degree every 71 years. So in 200 years, it'll be 3 degrees. And you can start to measure that. So he noticed this by comparing his measurements with Babylonian ones. By the way, what is the wobble, this kind of wobble of precession of the equinoxes actually due to? So scientists these days understand it the following way, that the sphere, the Earth is actually not a perfect sphere. It's actually a little bit more bulging at the equator than at the poles. This was a very important question back in the 17th, 18th centuries. They wanted to know whether the Earth was sort of flattened this way or flattened this way. You know, whether it was more oblong in this direction or was sort of wider. So, and there was an important controversy, and Newton had one position, other people had others. But they actually had scientific experiments go around the world to make various measurements to determine the actual nature of the Earth. It was an important French expedition that resolved this question. And they found that, in fact, Newton was right, that the Earth was a little bit extended along. There was an equatorial bulge. Okay, so since there's a little equatorial bulge, it means that the sun's attractive force, if the thing is like this, the attractive force is not entirely uniform, because let's say that things are tilted like this, then that bulge down there is being attracted, and so there's a kind of a gravitational force that's wanting to push it this way. And also the moon also has a gravitational force that affects that wobble. So that's sort of the explanation in that direction. Okay, so we can see that the story is quite interesting, but this is really a modern point of view, right? This is a story that we now have as a consequence of all kinds of brilliant people's observations and theories, and essentially thousands of years of understanding, especially the Copernican revolution, which brought this heliocentric theory into prominence. Although I should mention that a heliocentric theory was not Copernicus's idea originally. There were Greek people who supported this. There was a fellow called Aristarchus who had a heliocentric point of view. And in fact, there was also Babylonian astronomers who also had a heliocentric point of view towards what was going on. Okay, so that's all well and good, but now we have to come to what it was like for the actual ancient peoples. All right, so this story is far from the way they would have understood it, absolutely miles and miles away from the way they understood it. Okay, so we now have to almost forget what is contained in this picture and try to imagine what the world would have been like from the point of view of an ancient astronomer. So from an Earth-centric point of view, what actually do we see? Well, from an Earth-centric point of view, we're obviously stationary. Okay, you can see we're stationary. We can't feel anything moving. So the Earth is stationary. So here are some various observations that any sensible person would have made. The Earth is stationary. But the night sky rotates above it. Okay, and that's obvious. You just go out there and you have a look. You spend a few hours staring at the stars, and you will see that that's exactly what happens. So you go out and you look at the night sky, and we're talking about people who would have been a little bit, the these ancient civilizations, a lot of them would have been in the northern hemisphere, not too far from the equator, but in sort of middle latitudes, but still a little bit in the northern hemisphere. Okay, so you go out into the night sky and you see the northern stars, and what do you see? Well, okay, here's the night sky. You're looking at the night sky, and okay, there's all these constellations, just all these dots. Okay, so maybe here's some constellation that you think is a bear or something or other. But just really a configuration of stars. And then you're watching that, and then you notice that a little while later, it's maybe a couple of hours later, it's over here. It's moved. And the constellation that was over here has moved over here. And you can maybe identify that there's sort of maybe a star around there, which is more or less fixed. And so everything seems to be kind of rotating around this kind of direction. But what that effectively means is that this is sort of a big picture, but what they would have thought is that, okay, here is our Earth, okay, and here's Earth, and here is a sphere. So they would have deduced that the night sky rotates above it and that the stars are on a big sphere. Stars are on a, let's call it celestial sphere. So there's a big sphere that's outside there, which is basically the night sky, and it's rotating. And the stars are fixed on this celestial sphere. The stars are on a celestial sphere which rotates. So here's the celestial sphere. And so maybe the North Pole it's not going to be straight up here. Maybe the North Pole is in this direction. Okay, so north is in this direction here. So there's a kind of a rotation around this axis. This whole thing is rotating. Yeah?
Do you think there's anything beyond the sphere?
No, I don't think so. I mean, they might have speculated, but I think that was sort of as far as it went. Maybe there were some religious things that might have, they might have guessed as to what might have been beyond that sphere, but scientifically they wouldn't have any idea.
So did they just take the sun to be a big star on that celestial sphere?
Yes. So on the celestial sphere there are all these stars forming these various constellations, and then there are these other things as well. Okay, prominent amongst them is the sun. So the sun is something else that's attached to the celestial sphere. It actually makes the same kind of movement as the stars do. So if you watch all night long, you see that the stars are kind of coming up. They're coming up on the east, and then I guess the east is over here. Coming up in the east, and then going down in the west. Okay, this maybe here is maybe there is north. Okay, so it's sort of going like this. And so stars are rising here, and then you can follow them all night long, and then around morning time they pass the western horizon. And then around morning time the sun comes up in the same way, and it makes the same kind of trajectory that the stars did, and at the end of the day it goes down. And so you can observe that the sun is making the same kind of movement as the stars did. So the sun appears to be on the celestial sphere. And of course the moon is also somewhere there. It's also making the same kind of trajectory. So there's a moon over here, and there's a sun, and eventually you realize that there's also these other planets like Mars and Jupiter. But the difference between the planets and the sun and the moon and the stars is that the sun and the moon and the planets are actually moving on this celestial sphere. They're not in fixed positions. So we get a picture that looks a little bit more like this. Okay, by the way, they also would have deduced that the Earth was round. So all the ancient astronomers basically knew this. None of them thought the Earth was flat. They all knew the Earth was round. There's lots of evidence for that. I mean, if you have stars which are going, you can see them going all night long, and they're going like this, and then tomorrow they come up that way again. How is that possible? Right? Obviously, they're attached to a big sphere that goes around us there, and then it comes, underneath us, and then around that other side. So obviously, we're a kind of a sphere, and the celestial sphere is surrounding us. Other evidence for the spherical aspect of the Earth is found with sailors. So when you're at sea and you're watching a ship sail away, it goes to the horizon. Once it's near the horizon, you see its sails, and then eventually its hull dips down, and you see the sails. It's not as if the thing just gets uniformly small as it would be if it was a flat thing. The top of the ship is visible once the bottom of the ship is no longer visible. Same with an island. If you're approaching an island, you see the mountain top of the island before you actually see the base of the mountain. That's because it's round. And the other evidence for that was in a lunar eclipse. When the Earth gets in the way of the sun's rays on the moon, if you have a full moon, where the sun is shining directly on the moon is full, and then the Earth happens to get in the way, then it's going to cast a shadow. And it's obvious that shadow is round. You can see there's a round shadow that traverses the moon, which is the shadow of the Earth. So you can see the shadow, it's the shadow of the Earth. So the Earth is round.
And the stuff that Earth was flat thing.
No ancient astronomer thought that way. That was just the lay person who knows nothing of science. Some kind of primitive belief that they would have had, but no. So the Earth was round. They all knew that. So here's the Earth. And around this Earth is then this sphere. Okay? And so we'll put the sphere is rotating. Let's put the north pole of the sphere here. So here's the Earth. And here's the celestial sphere. Okay, so everything is really happening on this celestial sphere. And that's why spherical geometry plays such an important role. But it's not the sphere that's the Earth. That's not the important sphere in astronomy. The important sphere is the actual sphere of the night sky. Okay, we know it's not actually a sphere, but it certainly looks like it's a sphere. We can see why the ancient peoples would have thought of it as a sphere. So there's a sphere on which all the stars are pinned and the stars are fixed, and this sphere is rotating. And it rotates around once a day. And because there's a natural direction, a north, and in fact in the northern hemisphere there's actually conveniently a star called the North Star, which is almost exactly in that direction. So that's fixed under the rotation, so it makes it very easy to see where north is, at least these days. So then there would have been an equator. So the equator of this celestial sphere would be this great circle of this sphere, which is just perpendicular to the north direction. Now, there's also the sun and the other planets. So here there's another line, which is another great circle. And this is the path of the sun. Okay. So if we think of this, this whole sphere is rotating. Yes, it's rotating around once a day. But still, if we take that into consideration, the sun itself is moving on this sphere. We know that because it's actually the case that we're actually moving around the sun, and over here, the sun's in a different direction with respect to the stars than it was over here. It's in exactly the opposite direction. Right? In terms of the celestial sphere, the sun is that way, and over here, the sun is in that direction. So if you're always pointing towards the sun, as you're going around, the sun is now in a different position. So the sun is actually wandering around this great circle, and that circle is called the ecliptic. And that's at 23 degrees. And that really represents the plane in which we're traveling. So not just the sun is on this thing, but almost all of the other objects, the planets and the moon and so on, are in a sort of a relatively small band around the ecliptic. So around the ecliptic, there's the moon somewhere, depending on what time of the month it is. There's the moon. And somewhere on this ecliptic are also Mars and Jupiter and the other planets, the other five planets. So all the planets are basically on this ecliptic. Now, but they're moving, right? They're moving on the ecliptic because the sun goes around this thing once a year. The sun goes around once a year, more or less uniformly, pretty well uniformly. Well, the moon is doing its thing, okay? It's going around once a month, but so it's moving more vigorously than the sun. The moon is changing its position from day to day. From day to day, you can see the moon is in different position. As you can see also when you go out to the night sky, every day the moon is, maybe a degree or no, more than a degree. 360 divided by 27, so about 12 degrees further on than it was the night before. Right, the moon comes up later and later during the night. So the moon is doing its thing, but what's much more peculiar is the planets. So the sun and moon activity is somewhat regular, but the planets are more mysterious. In particular, the planets do strange things. For example, if we look at Mars, let's say. So Mars will do something like this. It'll go in this direction, and then it will loop back for a little while. And then it'll head back in this direction again. So it does strange things. It just goes like, it makes these kinds of trajectories. The planets are doing these crazy things. And if you observe the planets night after night and you keep careful tables, and these ancient civilizations ended up doing that, they became very interested in where things were on a regular kind of basis, and they kept tables, they kept track. Then you can start to, kind of predict where things were in times in the future. The planets are very hard to predict. The moon and the sun are, as we say, relatively regular. In fact, there's this important kind of regularity that happens. So with the sun and the moon, maybe I'll just put it up here. The sun and moon, they obey this something called a Saros cycle. Okay, so there's a Saros cycle of 18 years. So roughly every 18 years, the relative positions of the moon, earth, and sun get back to where they started. And that makes predicting eclipses much easier. Okay, so we have these two great circles, but the story is not finished because there's also us. All right, we are actually on this earth somewhere. Maybe you have built yourself an observatory, a big flat circle, carefully marked, maybe with some structures above it, with some metallic frame that allows you to measure where things are at various times, and you can kind of see all the way around. So then part of your story is that there's going to be a horizon. So if you are maybe here, then let's put you up. You probably think of yourself as being on top of the earth, right? Then there's a horizon. So that's another circle that's important. The actual horizon of where you are, what you actually see. And so we can see some of the complexity that these people were faced with, because at the very least, we're talking about the geometry of a sphere with 3 great circles drawn on. This is not supposed to be anything like that, but so here's a great circle. You know, you can imagine 3 great circles representing these 3 conceptual lines. And then you want to understand what's going on in terms of that system. So, for example, you might want to have coordinates. Let's say here's a star that you're interested in. Okay? So you want to give coordinates to that star. One way of doing that would be to measure how far down you are to the equator and how far over you are to this point here. So this point here is sometimes written maybe with V. This is what corresponds to a vernal equinox. So the place where the equator of the celestial sphere's rotation crosses the ecliptic. There are going to be 2 of these. There's one on this side and one on the other side. Over here. These are the equinoxes. These are the sort of the times when there's as much sun in the day and at night. And they're sort of natural reference points. So a natural thing to do would be to measure along this direction, maybe call it alpha. And this thing here, say delta. So these would be called equatorial coordinates, where alpha is called the right ascension. And because it's measured on the equator, it would be measured in hours. So 0 to 24 hours from the equinox V. And delta would be the declination, sort of how far above the equator or the equator of the celestial sphere a star was. And these would have been, so we're typically measuring in angles here. Angles are the natural thing because of the rotation being uniform. And basically the Babylonians established their angular system, and that's been basically used by astronomers since then, at least in the Western world.